In this second module of Chapter 10, Module 10.2, I cover health and health span concepts using a multi-stage model applied to non-human species. There are at least 4 reasons why basic health span studies on non-human species are important. First, identification of system failures. Functional senescence studies will identify key organ systems that fail with age, some of which may be directly involved in survival or tied to impaired functional status, but not mortality. Second, establishing connections between lifespan and health span. Studies of functional senescence can shed important light on the mechanistic connections between lifespan and health span. For example, it is often not clear whether manipulations that extend lifespan affect systems equally or selectively. Third, biomarker identification. Studies of health span have the potential to identify biomarkers for aging and health. Such biomarkers will allow researchers to assess whether an intervention aimed at extending lifespan or health span is effective. Fourth, intervention concepts and techniques. Given that older adults often prioritize late life functionality over life extension, studying functional senescence will help identify the pathophysiological changes associated with aging. This will further our understanding of how these changes affect both health span and lifespan in order to ultimately identify interventions that lessen the adverse effects of age on health status. In this module, I present as a case study an overview of assessment and scoring methods for health in the African buffalo, a species whose populations experience drought stress virtually every year and severe stress every several decades when dearth conditions become extreme, as occurs in the African savanna. Rather than focusing on individual level measures, conservation biologists have traditionally approached health in non-human species in the wild based on population change, where increasing populations are considered healthy and decreasing populations as unhealthy. However, in an attempt to identify the mechanisms underlying these population changes, the focus can be shifted to assessing the health of wild animals that are based in part on the health literature in the veterinary sciences. For example, studies of many species have shown that body mass and annual survival is highly correlated, particularly during the winter. Criteria for describing the health state and risk of death are presented in this table. Note that there are 5 different categories related to growth and health that I will use as stages in the model. This is because each category corresponds to a different level of risk. Note the main column of adult health description, in which contains the descriptions of different visual and behavioral characteristics of health category. The first category is stage of newborn or juvenile, in which risk is high to moderate. The second category is mature adult for health category number 1. This category corresponds to relatively low risk. The next category is mature adult health category, to which corresponds to elevated risk. The fourth category involves deteriorating health and thus high risk. In the last category, as senile adult, this corresponds to very severe risk. This life cycle chart shows the different health stages for the African buffalo, the between stage transitions, and the multi-stage model transition matrix. Here are the first 2 stages and their within and between stage transition directions. And here is the transition matrix for the entire multi-stage model. Stage 1 can transition to stage 2, and both stage 1 and stage 2 individuals can remain in those stages. This shows the next set of transition to the subsequent stages. Note that stages 2 and 3 can transition to subsequent stages. They can remain in each of their respective stages, or they could revert back to less healthy stages. The individuals can either transition to ultra-frail stage, they can stay in that frail stage if they're already in the stage, or they can revert back, at least in principle, to a slightly healthier stage. The output of this model is shown here, where in the first column we have stage, then the next column age, then the number alive at age X, survivorship, and then 5 stages, including the pre-adult and 4 different adult stages based on health status. Note that a huge amount of overlap exists at any age with respect to health status of individuals. This is especially true around 15 years of age. By 20 years and after, virtually all individuals are in the severe to ultra-high risk stages of health. Note that according to this hypothetical life table, the expectation of life for African buffalo subject to these mortality and transition rates is 7.5 years. The average individual spends 48%, 39%, 4%, 8%, and 2% of its life in the pre-adult stage in each of the 4 respective adult health stages. Several aspects of the model schematic and the table output merit comment. First, these illustrate differences in the ages at which individuals may transition between stages. For example, not all individuals become sexually mature at the same age, nor do individuals transition to different health states at the same rates. Second, death rates may differ drastically among individuals of the same age who are in different health states. For example, the hypothetical multi-state life table shows that individuals that are between 14 and 18 years are distributed across all 4 health stages, and their risk is less determined by their chronological age per se and more by their health status. Some individuals in this age range are subject to low risk, whereas others are subject to acute or severe risk. Third, it is likely that individuals, cohorts, and populations of buffalo can transition both forward and backward across multiple health stages as environmental conditions change. Individuals experience ever-increasing stress and thus heightened health and mortality risk as the herds move across increasing distances between vegetation for grazing and water sources. One take-home message for the use of health demography methods in research and wildlife management and conservation biology is that the tools and concepts used in human health demography can be adapted for use in the systematic study and analysis of health in populations of non-human species. With respect to African buffalo, only around 2% of the populations are disease-free, and incorporating this information into a broad analysis of health dynamics in wild populations may shed important light on their mortality dynamics. Just as in human populations, different diseases in wild populations of non-human species may have little impact on mortality risk under certain conditions, but they could have dire mortality consequences under conditions such as severe drought. Similarly, some diseases may serve as underlying causes of death in the wild, other diseases may be contributing causes of death, and still other diseases may be intervening causes of death. Though across all of these hypothetical cases, it is likely that predation would be the immediate cause of death in most cases, which for the African buffalo would be predation typically by the African lion. This ends Module 10.2 on this example of applying multi-stage modeling concepts to health conditions in a non-human species. In the next module, I will show a slightly different but related stage-based model applied to health-related conditions in a fruit fly.